Section 10.2, we're going to look at hypothesis tests for a population. Our first objective is to explain the logic of hypothesis testing. So let's look at an example. A politician hires a polling firm to obtain a random sample of 1,000 registered voters in her district and finds that 534 are in favor of a specific policy. So the proportion in favor is 534 over 1,000, or 0.534. Recall that lowercase p is the sample proportion. Do these results suggest that among all registered voters, more than 50% favor the policy? Or is it possible that the true proportion of registered voters who favor the policy is exactly 0.5 or 50%, and we just happen to survey a majority in favor of the policy? In other words, would it be unusual to obtain this sample proportion or a higher one from a population whose proportion is 0.5? What is convincing or statistically significant evidence? So this is kind of the idea of hypothesis testing. We want to make sure that we don't just have a fluke in our sample and are trying to use that for the proportion. So let's answer that question. Would it be unusual to obtain the sample proportion of 0.534 or higher from a population whose actual proportion is 0.5? Okay. To determine if a sample proportion of 0.534 is statistically significant, we need to build a probability model and then see what the probability of getting those scores or those responses is. When observed results are unlikely under the assumption that the null hypothesis is true, we say the result is statistically significant and we reject the null hypothesis. Okay. So this is, again, what we're looking for is this kind of indicator that we have enough statistical information to overrule the null hypothesis and to kind of rule in favor of the alternative hypothesis. Since the sample data is from a simple random sample, our calculation of NP times 1 minus P is greater than or equal to 10, and the sample size is sufficiently smaller than the population, we can use a normal model to describe the variability in p hat. The mean of the distribution of p hat is equal to the population mean mu sub p hat, which equals 0.5. That's from our null hypothesis. And the standard deviation of p hat is sigma p sub p hat, which is the square root of p times 1 minus p, the proportion, all over our sample size. And here we get 0.016. So we have a mean of 0.5 and a standard deviation of 0.0. So here we can see the sampling distribution of the sample proportion of the politician example. So we have the mean, and then here we have one standard deviation above and below. Okay. We can consider the sample evidence to be significantly significant. Boy, I'm having problems pronouncing this morning. We can consider the sample evidence to be statistically significant or sufficient if the sample proportion is too many standard deviations, say 2, for example, above the assumed population proportion. Recall, we just looked at and we saw, I'm sorry, I went a little blank here. We can calculate our z-score, which is our p hat, given in the problem, 0.534, the population, the proportion of the sample, minus the mean, all over our standard deviation, which we just calculated. Okay? And so we get a score of 2.15, a z-score why does it make sense to reject the null hypothesis if the sample proportion is more than 2 standard deviations away from the hypothesized proportion? That actually is a good question, right? Because it seems like if it's really far from the mean, then why would that be statistically significant? What would be the basis for supporting that? Because it seems more like an outlier, right? Well, the area under the standard normal curve to the right of z equals 2 is 0.228. Okay. If the null hypothesis were true, then 97.72% of all sample proportions will be 5.532 or less, and only 2.28 of the sample proportions will be more than 0.532. If the sample proportion is too many standard deviations from the portion stated in the null hypothesis, we reject the null hypothesis. A second criterion we may use for testing is to determine how likely it is to obtain a sample proportion of 0.534 or higher from a population whose proportion is 0.5. If a sample proportion of 0.534 or higher is unlikely or unusual, we have evidence against the statement in the null hypothesis. Otherwise, we do not have sufficient evidence against the statement in the null hypothesis. We can compute the probability of obtaining a sample proportion of 0.534 or higher from a proportion, again, this is what we just saw before. We already know that we can use the normal model. Here, the probability that p hat is greater than 0.534 is the probability of the z-score being greater than 0.215, which is 0.158. Okay, and this is from the table 5. I'm sorry, this is 1 minus the table 5 z-score, right? Because remember, table 5 gives us the area to the left. And this is called the p-value, which means approximately 2 samples in 100 will give a sample proportion as high or higher than the one obtained if the population proportion is 0.5. Because these results are unusual, it's only 1.5%, we take this as evidence against the statement in the null hypothesis. If the probability of getting a sample statistic as extreme or more extreme than the one obtained is small, under the assumption the statement in the null hypothesis is true, then reject the null hypothesis. So again, if it's very unlikely that we're going to get a sample statistic, if the probability is low, then we reject the null hypothesis. A p-value is the probability of observing a sample statistic as extreme or more extreme than one observed under the assumption that the statement in the null hypothesis is true. What we might say here is the p-value is the likelihood or the probability that a sample will result in a statistic such as the one obtained if the statement in the null is true. Okay. So this is a great table to have. If the p-value is greater than 0.1, do not reject, 0.10, right? That's 10%. Do not reject the statement in the null hypothesis. The sample evidence is consistent with the statement in the null hypothesis. If it's between 5 and 10%, there is some evidence against the statement in the null hypothesis. If it's between 1 and 5, there is moderate evidence against the statement in the null hypothesis. If it's between 0.1% and 1%, then there's strong evidence against the statement in the null hypothesis. And if the p-value is less than 0.1%, there is very strong evidence against the statement in the null hypothesis. The lower the p-value, the stronger the evidence against the statement in the null hypothesis. Okay, so if we have a probability greater than 10, we're not going to reject it. On the other cases, we would have some evidence, and you would use really this language. There's some evidence, moderate evidence, strong evidence, or very strong evidence against the null hypothesis. Remember, we don't ever reject fully the null hypothesis. We just make it as a statement that we don't support it, etc., and that this would be the way to say it. There's moderate evidence against, or etc. The figure illustrates the political situation for both the classical, which was the z-score, and the p-value approaches to hypothesis testing. Okay. We reject the null hypothesis that p equals 0.5 and conclude that p is greater than 0.5 as indicated by the distribution. The distribution with the blue line, it's the blue line, okay, not the blue area, shows the distribution of the sample proportion, assuming the statement in the null hypothesis is true. The sample proportion 0.0534 is too far from the assumed population, proportion, of 0.5. Okay, it's too far away. So this lecture is about 40 minutes. So it's a good time to take a break, get up, get a drink, get a coffee, walk outside, take a 15-minute break, and then come back and finish the lecture. Our second objective is to test hypotheses about a population proportion. So our first step is to determine the null and alternative hypotheses, and we know that these can be structured in one of three ways: left-tailed, right-tailed, or two-tailed, depending upon whether we're using less than, greater than, or not equal to. Then we select a level of significance alpha depending on the seriousness of making a type 1 error. So it really depends upon what we're looking at statistically. And then we continue with steps through 5, provided that the sample is the simple random sample, that the sample size is large enough and small enough, right? Somewhere in that middle. And we know how to do that between the 5% rule and calculating our sample size with the proportion, making sure it's greater than or equal to this factor of 10. In the classical approach, we compute the test statistic. Z sub naught equals p hat minus p naught all over the square root of p naught times 1 minus p naught over n, which of course is the standard deviation. And then we use the table 5 to determine the critical value, again depending upon whether it's two-tailed, left-tailed, or right-tailed. We're going to have different critical regions. And then we compare that critical value with the test statistic. If z sub naught is less than z alpha, negative z alpha, or greater than z sub alpha over 2, we reject the hypothesis. If z naught, our critical value, if our calculated value z naught is less than negative z naught, we reject the hypothesis. This is left-tailed. And if z naught is greater than z alpha and it's right-tailed, we reject the null hypothesis. Remember, the z alphas are all the critical values for the classical approach. In a p-value approach, we compute the test statistic in a similar way, and then we use table 5 to determine the p-value, right? The area under the curve, which is then the probability. And notice that if we have a two-tailed, then we're looking for a p-value that's twice, right? Because we have the left and the right. And then we can see the probability. And we just saw the table for what we would do with the null statement based upon the level of probability being greater than 10 and all the way down less than 0.1%. Okay. So statistical value just says, the same thing we did here. How to find the data. We don't do it by hand. And if the p-value is less than alpha, reject the null hypothesis. This is a great table that's in your text, and I would suggest reading through that section with the example. So let's look at a right-tailed problem. Humira is a medication used to treat rheumatoid arthritis, RA. In clinical trials, 705 subjects diagnosed with RA were administered 40 milligrams of Humira every other week. Of the 705 subjects, 66 reported nausea as a side effect. It is known that the proportion of RA subjects in similar studies receiving a placebo who reported nausea is 0.08. Does the sample evidence represent significant evidence that a higher proportion of subjects receiving Humira experience nausea as a side effect than those taking a placebo? We're going to use alpha equals 0.05, 5%, because this is pretty important, right? This is a medical study. The null hypothesis would be that the proportion of subjects taking Humira who experience nausea is 0.08, the stated proportion. We want to determine if the sample evidence suggests that a higher proportion of subjects taking Humira experience nausea. So then we would use the greater than symbol, right? So the H null is that our proportion is 0.08. 66 divided by 705 versus our stated hypothesis that we believe that people actually taking Humira is higher than that given statistic, given parameter. The level of significance alpha equals 0.05. The data result from a random experiment. Here I've made sure that we can use these approaches, the normal approach. So for the classical approach, we assume the statement is true. The sample proportion experiencing nausea is 0.94, which is just the observed people with the observed characteristic over the population. We want to know if it's unusual to obtain a sample proportion of 0.094 or higher from a population whose proportion is 0.08. Okay, that's our null statement, right? 0.08 is what the population equals, and we want to see if this is statistically significant to reject the null hypothesis. So we calculate our z-score, z0, and we get 1.37. Okay. Because this is a right-tailed test, determine the critical value of alpha, 0.05 level of significance, to be z equals our z sub alpha, which is z sub 0.05, which equals 1.645. Okay, remember the z alpha is that area to the right. Because the test statistic is less than the critical value, 1.37 is less than 1.645, we do not reject the statement in the null hypothesis. Notice that this test statistic does not fall into the critical region, okay? The critical region is this area here, so if it fell in there, then we'd be okay. While we do not reject the statement in the null hypothesis that the proportion of Humira subjects experiencing nausea is 0.08, the p-value suggests that there is a moderate evidence to suggest that Humira users are experiencing an adverse reaction that is greater than the 0.08. If we take the p-valued approach by hand, again, we have to go through the first two steps again to validate the data as normal and do some calculation. Assume the statement in the null hypothesis is true, again, that p sub 0 equals 0.08, and the sample proportion p hat is 0.094. We want to know how likely it is to obtain a sample proportion of 0.094 or higher from a population whose proportion is 0.08. So the test statistic that we're going to calculate, Z0, again, is 1.37. Because this is a right-tailed test, the p-value is the area under the standard normal distribution to the right of the statistic, Z0. which is found by 1 minus the Z0 value entry in table 5, which equals 0.853, okay? Here again, we have the same data, or relatively close. It's not the same data. The p-value of 0.885 Han means that if the statement in the null hypothesis is p equals 0.8 is true, we would expect to observe 66 or more subjects who experience nausea in about 85 out of 100, or 1,000, excuse me, repetitions of this study. The observed results are moderately unusual. However, because the p-value is greater than the level of significance, 0.085 greater than do not reject the statement. And that was one of those values in the table when you're doing the probability, okay? So there's not sufficient evidence at the alpha equals 0.05 level of significance to conclude the proportion of subjects taking Humira who experienced nausea is greater than 0.08. So even though we had what looked like a statistically high probability of 0.08, that's 8%, that's not so low, right? That's between the 5 and the 10. So there was some evidence to reject the null, but because there's that caveat that if the p-value is greater than alpha or the level of significance, we do not reject the statement in the null hypothesis. And that would be a really good kind of conceptual piece. Why is that so? What is the concept behind that if our level of significance is 5%? And so again, remember what we're doing there is we're talking about the probability of something happening. And so that, the higher the stakes, the higher the level of significance, right? Because an alpha of 0.05 means that you're 95% confident. So if you're already kind of taking into effect some of these other probabilities. So let's look at another example and see how we can step through this process again. Which do you think it's easier, to raise a boy or a girl? When asked this question in 1947, 24% of all Americans said raising a girl was easier. In June 2018, the Gallup organization surveyed 1,500 adults, Americans, of which 408 felt it was easier to raise a girl. Does this result suggest the proportion of adult Americans who believe it is easier to raise a girl has changed since 1947? So the null hypothesis would be that the proportion of adult Americans who believe it's easier to raise a girl is the same as it was in 1947. So in this case, our parameter, our sample statistic, would be 0.24. Remember, the null hypothesis is always a statement of no difference. So we're saying that in 2018 it was the same as 1947, and in 1947 it was 24% or 0.24. Also pay attention that this is a two-tailed hypothesis test, so we're looking for the areas or the probabilities at each end of the normal curve. So our null hypothesis is that our proportion, our sample proportion, is 0.24. Our alternative hypothesis is that it's not 0.24. It's not above or below. I mean, it's either above or below. Okay. It's not just greater than 0.24. It's not just less than 0.24, or at both ends. It's just different. Okay. The level of significance here is 0.05. That's just been assigned. And the independence tests, you can look in the book. This is where you see, was it random? Was the sample large enough? Was the sample not too large, greater than 5%, etc. So you can look at the book for those. I'm not going to walk through those steps again. Okay. So our next step is that if we assume the null hypothesis is true, then our sample statistic is p sub 0, and our p hat, our actual probability from our sample, was 0.272. So we want to know if the survey that Gallup did in 2018 is unusual, or is it just part of a parameter? So we want to know if it's unusual to obtain a sample proportion of 0.272 from a population whose proportion is 0.24, okay? So again, our null hypothesis is assuming this is true, that the proportion of the population even in 2018 is believes that it's easier to raise a girl is at 0.24 or 24% still. When we did the sample, our p hat, right, our sample proportion is 0.272. So this is different, and so we want to find out, is this what statistically is there statistically significant data to support this or to deny it? Okay, so the first thing we need to do is, using the classical approach, is to find the test statistic. Okay, and remember, this is our sample proportion minus our assumed proportion, our population proportion, divided by the standard deviation of that population proportion. Okay, and in this we get a z-score, a test statistic, a z-score of 2.90. Okay. Because this is a two-tailed test, we're looking for scores that are above 2.90 or below 2.90. Okay. So, with our level of significance, alpha being 0.05, this gives us a z sub alpha over 2 of plus or minus z sub 0.025. That's 0.05 divided by 2, right? Nothing stretched there. And what we get here is plus or minus 1.96. And this comes from table 5. Now remember, when we're looking in table 5, we're looking for this z-score, 0.025, or negative 0.025. And then finding the z, we're looking inside the data for this entry, 0.025, and then we're seeing what z-score comes up, okay? The outer edges, the column and row titles, to get that z-score, okay? So you can still use table 5 to find these critical values. You don't need to just memorize the 3 that I told you about before, the 90, the 95, and the 99, okay? So you can find these again going into your table 5, looking at the data entries that correspond with 0.025, and then seeing what the z-score is by the row and column titles, okay? And so we can see here that here is the z-score of 1.96, and here's the z-score of negative 1.96, okay? You can see that they're just shy of 2 standard deviations, all right? The critical regions are the ones that are highlighted above or below those, okay? Because the test statistic, the 2.90, lies within the critical region, 2.90 is greater than 1.96, we reject the statement in the null hypothesis, okay? We reject the statement in the null hypothesis. We can also do the same problem using the p-value approach, okay? Still following step 1 and step 2. And basically step 3 is sort of the same, right? We first start out with the null hypothesis, p sub 0, is the population parameter is 0.24, and the sample proportion is 0.272. And when then it's the same thing we're trying to find out. Is that unusual to find this in a sample given that the actual population proportion is 0.24? Okay. We still want to find the test statistic first, like we did in the prior example, so I'm not going through that calculation. It's the same one. Now remember that in a two-tailed test, the p-value is the area under the standard normal distribution. And because it's two-tailed, it's the value to the left of negative 0.290 and to the right of 2.90. Okay. Since we know this is a normal distribution, we know that the probability of less than negative 0.29 is the same as the area or probability above 2.90. So we can kind of just find one of these probabilities and then multiply it by 2. Okay. Well, the probability of greater than 0.290 is 1 minus 0.9981. Okay. So here what we're doing is we're looking at the z-score again in table 5 of 2.90 over here. And we get this entry into the table 0.9981, which remember is the area to the left of that. Might have been easier to find this one because then I wouldn't have to subtract it from 1. I wasn't thinking about that when I built this. And so we get the area that's greater than, the area in the region that's greater than 2.90 is 0.0019. Remember, this area also represents the probability. So the probability of getting either of these would be the same probability for each times 2. So twice this is 0.0038, which if you think about that, that's 38 1,000ths. No, I'm sorry, 3.8 thousandths, or a percentage of 0.38. So that means there's a likelihood of, if we did a sample of we did 1,000 samples, that 4 out of those samples would have that result in it. Assuming that 0.24 is the population proportion. This, of course, is a very, very small probability. Also, we can see that as our probability, our p-value of 0.0038 is less than alpha. Remember, that's one of the conditions where we also would reject the null hypothesis. If we did this using technology, specifically StatCrunch, we can also see that the p-value is 0.0037 and draw some of the same conclusions. The last thing we need to do is to state that conclusion, and you see it here in step 5. There is sufficient evidence at the alpha equals 0.05 level of significance to conclude the proportion of adult Americans who believe it is easier to raise a girl has changed since 1947. In fact, we are 95% confident, again that connects to the alpha equals 0.05, the proportion of adult Americans who believe it is easier to raise a girl is between 0.249 and 0.295. One of the last things we're going to cover in this section is how to test a two-tailed hypothesis using confidence intervals. When testing the null hypothesis is p equals p0, or the population parameter equals the sample statistic versus the population parameter doesn't equal the sample statistic. If the confidence interval contains p sub 0, which is the population parameter, we don't reject the null hypothesis. But if it doesn't contain it, we conclude that the population parameter doesn't equal the sample statistic at the level of significance of alpha. Okay, so this is like kind of a shortcut test for hypothesis testing with a two-tailed hypothesis, okay? If the confidence interval contains our p sub 0, then we don't reject the null hypothesis. If it does not contain it, then we can conclude that the population parameter proportion doesn't equal that p sub 0 mark at a specific level of significance alpha. So let's look at how that works. A 2009 study by Princeton Survey Research Associates International found that 34% of teenagers text while driving. Does a recent survey conducted by Consumer Reports, which found that 353 of 1,200 randomly selected teens had texted while driving, suggests that the proportions of teens who text while driving has changed since 2009. Use a 95% confidence interval to answer the question. So let's do some calculation. Our proportion sample statistic, our sample statistic, P, is going to be 353 divided by the 1,200, right? That's our proportion given, which gives us 0.294. At a 95% confidence interval, our alpha is going to be 0.05, so alpha over 2 is 0.025, and this gives us a z sub alpha over 2 of 1.96. Remember that our confidence levels are our parameter, our proportion, plus or minus the margin of error, and our margin of error is found by multiplying z sub alpha over 2 times the square root of our proportion statistic times 1 minus p all over n and the square root of that quantity. So if we calculate we have our p-value here. If we calculate the error, it becomes 0.296. I'm not going to do that. And so when we add that, did I say that right? I'm sorry, 0.026 is the error calculated. When we add or subtract that from 0.294, we get a confidence interval with a lower bound of 0.268 and an upper bound of 0.320. Okay, because the null statement uses 0.34, and because 0.34 or 34% or 0.34, and because this is not within the confidence interval between 0.268 and 0.320, there is sufficient evidence to conclude that the proportion of teens who text while driving has changed. So again, what we've done here is we are kind of refuting the null hypothesis that it hasn't changed, and we have sufficient evidence because that point of reference is outside of the confidence interval. Okay. Our third objective in 10.2 is to test hypotheses about a population proportion using the binomial probability distribution, and this is used when our sample size is too small, and so it doesn't pass those parameters of the formula that has to be greater than or equal to 10. And we're not going to be covering this method in this course, but this is typically used for really small sample sizes. And so if you do become a statistician, I'm sure you'll see this again. But I did want to kind of just point out that this objective focuses on those smaller sample sizes so that we could still test a hypothesis.